Uh, it, it is now 10:30 in Moscow and 3:30 in Beijing, and I'm happy to start out today's seminar. Our speaker is Arina Filimonova from St. Petersburg, and she will tell us about morphisms generating Lyndon words. Let's welcome.
Right. Thank you. Hello, everybody. Everybody hears me, right?
Yeah.
So yeah, that's right. My name is Arina Filimonova, and I'm telling about more. I'm going to speak about morphisms generating Lyndon words. Let's see. Let's start with some basic definitions. What do we call morphism? A morphism is a map from. Let me just give some explanations here. Can I? Yeah. So what is this? Sigma is some finite set. It will be our alphabet. We'll be calling it alphabet. It's a set of letters. Some finite set. We will have as an alphabet. And this sigma with the star is the set of all finite words of the alphabet. Of the alphabet sigma. So for example, if sigma contains just two letters A and B, we can create some words or some word of that. It would be contained in this set. Like all other finite words, we also have a special finite word which will be denoted like that, like epsilon. It's an empty word which contains no letters. There is such word. There is just no letters. All other words contain at least one letter. So, okay, what is a morphism? Morphism is a map from the set of all finite words over some alphabet sigma into the same set. I mean, it could be generalized. So this alphabet could be some different alphabet. It don't have to be sigma, but for us, for our considerations, these two alphabets are the same. But it doesn't have to be like that. But for us, it will be like that. Map F is from the set of all finite words over sigma into the same set is called a morphism if it preserves the operation of concatenation. So like this. If some word can be written as concatenation of two different words, then f of this word must look like this: a concatenation of the images of these two different parts, these two parts of the word. So as you may see already, it is enough to define a morphism just on the letters of the alphabet sigma. All right? Because
excuse me.
Mm-hmm.
I'm sorry. Then for sigma star, we do not allow the inverse of alphabet.
For sigma star, you don't.
In sigma star, we do not allow inverse of alphabet.
What is an inverse?
Oh, I mean, a to the -1.
Inverse
like
elements.
No such operation.
Sure.
It is a monoid.
Okay.
We have we can consider it as a monoid with operation of concatenation. Sure.
Okay, thank you very much.
We know what does it mean to multiply them, but there is no this for this operation, right? So it's not a group for our considerations. No, no group structure, nothing like that. Okay. So you see, as this holds, as F must preserve the concatenation, it is enough to define F on letters of the alphabet. You see, because everything from here, any finite word over sigma consists of letters. It consists of letters, so if we know where each letter maps, we know that any word consisting of these letters maps into concatenation of the images of the letters, right? So we only, from now on, we will define morphism on the letters. And the thing also always holds, also due to this. So we know that empty words goes into empty words, and if we know where each letter goes, we know the morphism is completely defined. Okay, let's go next. Let's move on. Oh, somebody else. Okay.
Arina?
Yeah,
thank you very much, but I will accept them. Yeah, you do not need to care them.
Okay, thank you very much. Okay. So,
what do you mean by non-erasing? What do you mean by non-erasing?
Yes, that's right. I'm going to explain. Let F be non-erasing morphism. What does it mean? It means the following: there is no letter that goes into an empty word.
Okay.
We can say it like this. Yeah. It just so what does it mean? It also means that the length, the just amount of letters. Okay, so when you take the image of you, it never makes the word small. So it doesn't erase anything, if you will, because every letter goes into something non-empty. So each such image contains at least one letter.
Excuse me. For groups, we usually have presentations. Groups can act on something, and certainly monoids can also act on something. For example, on themselves. But maybe they can act on something. Some other objects. Maybe they have matrix representations or other interesting things. So can we convert this formal dynamics into dynamics of points in some space?
Well, yes, somehow. Okay, we can consider what do we do? We can consider okay. Let me just could you repeat the question, please?
Well, groups can act on something.
Yes, sure.
Monoids can also act on something. The question is, can we convert this formal dynamics of, say, limits and so on into some concrete dynamics when we have some, I don't know, a sequence of points, and we try to consider limits in some space or matrices maybe, or some other objects, not just formal words.
Right. You mean you've already like read it or? Yeah.
I mean, where can such objects act?
I can. Yeah, I mean, it's hard for me to answer right from just. I need to think about it a little bit. So, I mean, it's just like something I never thought about.
Well, you may just look in some, I don't know, Wikipedia, representations of monoids, representations of words. I think you can find something.
Okay.
Okay, let's go.
No, I mean, I'm looking for something a bit, but. Second. No, I have no nice answer for this for now. But I mean, maybe need to think a bit more. Okay. Well, let our morphism be non-erasing in this sense, and for some letter A, let this hold. What does it mean? It means that the image of A starts with A and continues with something non-empty. So it has length at least 2 and starts with A. So then you see. So then let's have a look. A maps to AU, which maps to AU f of u, if you will, which maps to, and so on. As you may see, it's absolutely like straightforward to prove that f of n, so it's f of a, f of squared of a, and so on. Nth power of f on a is a proper prefix, which means it is a prefix and it's not empty and it's not the whole word. F to the power of n of a is a proper prefix of the of the next power of f on A. You see, so A is a proper prefix of f of A, AU is a proper prefix of f squared of A, and so on. This will be the proper prefix of f cubed of A. So we can, some infinite word can be defined very well like this. How? Let's see how. It's just if some letter if in some position we have some letter is written already, it will stay there forever. You see, if we keep on taking images over f, this letter won't change because this thing is a proper prefix of the next power. So this letter never changes if it once occurs. So we can define some infinite words, some infinite word like this, because the length of this goes to infinity, because with each iteration the length grows at least. With each iteration the word gets bigger. So in every position, let's consider some I, letter on ith position will occur and never change. So that's how we can define an infinite word which generated by f starting with A. We will call this construction an infinite word generated by the morphism f starting with the letter A. F must be like this. So limit just in this sense, no topology here. I mean, there might be some topology or something, but it's just like you may consider this like this. So limit just in this sense, okay? Right. Was it understandable in some way? Oh, yeah, it wasn't.
No, it's okay. It's okay.
Right. So that is something we will call morphic word. Morphic word is a word like this. It's a word generated by morphism, some morphism f with this condition holding, and the word is generated certain letter rate for which this is true. Okay, that is a morphic word. I mean, usually it is called pure morphic, but we only consider such pure morphic words here, so let's call it just morphic here. But usually it's called pure morphic. And morphic is something more general. Oops. Sorry. Nobody sees my screen now, right? Just okay. Again. Okay. Let's see some example. It's just an example of some morphic word. Problem. What's the problem here? I can comment. Okay. Yeah, let's consider an example. Let's look at the very famous morphism. I don't know English. Thu Morse word is a word generated by this morphism, starting, for example, from the letter 0, but you see it's just symmetrical. So you can start with letter A as well, with letter 1 as well, and get the same word, but with respect to exchanging letters. But okay, let's consider this morphism and generate some words starting with the letter 0. Here it is. There are a lot of other definitions of the same word. It's a very famous word, but this is one of them. You can generate the Morse word with this morphism. It's just an example. Let's move on. Okay, let us define a Lyndon word.
Excuse me, can you hear me? I have a question that what morphism can get a period like a 1 0 get a period number.
You mean what? This word?
What morphism can we get a period number, rational number?
Period number.
Yeah, period number like 1 0 0 0 blah blah blah. What morphism can we get?
Okay, 1 0 0 0 and then
number. Rational number. Thank you.
You mean okay, you mean we want to get a string that represents some rational number, which means it's something. Which means it's something like something, and then something like this, right?
Yeah.
Okay. Yeah. The thing. Okay. Such words are called ultimately periodic, and morphisms generating ultimately periodic words are characterized. I mean, I'm afraid to say to tell some lies here, so I won't try to give you the right characterization. But morphism generating ultimately periodic words are characterized absolutely well and somehow easily. And yeah, this problem is algorithmically solvable. Algorithmically decidable, I should say in English. Algorithmically decidable. So by looking at the morphism, you can easily tell whether it produces ultimately periodic word. It's like it's a decidable problem if what you asked. So whenever you see a morphism, you can check whether it is producing something like that. And characterization is something. I mean, I can give you some references later where it's done. I will maybe at the end of the presentation give some references where you can read about this, but it's like only solved problem. Right. Right. Okay. So what is a Lyndon word? We need now to define a Lyndon word, we need our alphabet to be ordered, linearly ordered. Then a word over that linearly ordered alphabet sigma is called Lyndon word if it is lexicographically smaller than all of its proper suffixes. So let's see. Let's have a look at the examples. This word is Lyndon. Okay, yeah, why? Let's consider all of its proper suffixes. Let's start with this. Okay, this proper suffix is lexicographically bigger than our word. Why? Because our word starts with AA and this suffix starts with AB. You see, right? So the suffix is bigger. It's okay. It's okay. Let's check second suffix. Second suffix is this. It starts with B itself, and our word starts with A. So our word is smaller lexicographically than this suffix. Let's move on. We can consider this suffix. Once again, it starts with AB, while our word starts with AA. So, okay, now then we have two suffixes that starts with B. No need to check. Then we have an interesting suffix that starts with AA, but you see, this is a word AABB, and our word starts with AABA. So the word itself is smaller than this suffix. And then nothing to check. Once again, suffix starting with AB, and two suffixes starting with B. So the whole word, this is smaller than any of its proper suffixes. Then we call such word a Lyndon word. Let's have a look. This is not Lyndon. This is not Lyndon. Why? Because here we have this suffix that is lexicographically smaller than the whole word. It starts with AA, and the whole word starts with AB. And the last one is also not a Lyndon word. Why? We have this suffix, for example, and it's a proper prefix of the whole word, as you may see. So it is lexicographically smaller, once again. AAB is smaller than AAB something. So these two words are not Lyndon, and this is a Lyndon word. Okay, there were some studies around this about this Lyndon word. There is some famous algorithm. You can. I mean, I'm not going to talk about this because, first of all, I know little about this, and second of all, no time for that. Let's see one more example. A morphic word that is a Lyndon. So you see, this definition goes well as for finite or for infinite words, just the same definition. So these are finite Lyndon words or not Lyndon. And let's look at some morphic infinite Lyndon word. A word generated by this morphism starting with letter A is Lyndon. It needs some proof, but the proof, I mean, it can be easily proven. For example, you can prove the following, the following way. First of all, infinite word is Lyndon if and only if it contains an infinite amount of prefixes that are finite Lyndon words. Finite. That's like a simple thing. We won't need it later. So I mean, I didn't state it, and I'm not going to prove it, but it's another thing. It's easy to prove that some infinite word is Lyndon if and only if it contains an infinite amount of prefixes that are Lyndon words, finite Lyndon words. So this word being Lyndon can be proven like this. We can prove that just for each k, fk of a is Lyndon. You see, so our word contains all the prefixes of the looking like this of our word are Lyndon. So using this, we can tell that the whole infinite word is Lyndon. Something like that. So it's not a complicated thing. It's like if you try, it's easy to prove that this morphism really generates a Lyndon word. Start with letter A. Just an example. So sometimes morphisms generate Lyndon words, and sometimes not. Sometimes not. We can consider easily some more. I'm just improvising here, but it's quite easy. For example, something like this. You can just exchange this things here, and we won't get a Lyndon word then because our word will start with this, but somewhere in the word we will get such substring. I mean, let's look. The word generated by this morphism starting with letter A will start with this. So you see, we already have such a substring which says that this suffix is lexicographically smaller than the whole word. So okay, sometimes morphisms generate Lyndon words, and sometimes not. The problem is, we want to characterize the morphism generating Lyndon words. We want to be able to, like, just by looking at the morphism, tell whether this morphism generates Lyndon word or not. Okay, what is done in this problem? This problem happens to be somehow uneasy. Let's see what's done. The first thing that is done by some French mathematics is this. The problem is solved for binary morphisms, meaning the morphisms over the words on alphabet with 2 letters, binary alphabet. Let's see what is done for the binary in the binary case. the following theorem holds. Let f be a morphism over the binary alphabet, and let f meet all our expectations. We want this to be true, and we also want f of b not be empty. Like usual, we want our morphisms be non-erasing. Okay, then we can generate this word. We can generate an infinite word starting with the letter A. And what? And look, this word generated by morphism f starting with the letter A is infinite Lyndon word if and only if
can you comment on if part? So why are these conditions necessary? For example, the second condition.
Yes, I will easily comment on the necessity. All right. So let me just read it for once. This word is in infinite Lyndon words if and only if first it's not periodic. Then the third power of f on A is a prefix of a Lyndon word, some Lyndon word. And f preserves the lexicographic order on finite words, which means that just a simple thing. Third means this.
Well, it is written that it should preserve lexicographic order on all finite words. But why do we need that it preserves lexicographic order on all finite words? It's clear that we should preserve the order on words which appear as prefixes. Well, it's necessary, but why is it? So this is one thing, and the other thing is why? What about the condition 2? It looks very strange.
It's a great comment you have made. I will also comment on this later, on what you just said a bit later. But let's now look at the condition number 2. Okay, that's what you want, and it's obviously necessary because you look. If we want this to be a Lyndon word, right? Then look, this word has f to the power 3 of A as its proper prefix. So it just looks like looks something like this, where I should choose another letter, right? Some infinite word as well. So this word contains f to the power of 3 of A as its proper prefix, right? You see, because let me where is the eraser? Okay, I don't see the eraser here, but it's okay. Do you see this? That is because how this word was defined. You see, so we start with A, then we get f of A, then we got f to the power of 2 of A, and so on. And once again, each previous word is a proper prefix of the next. That's how we can correctly define this thing, and it has the third power of f on A as its proper prefix. So if we want this to be a Lyndon word, this must be a prefix of some Lyndon word. For example, this. You see? So it's definitely a necessary condition. It looks maybe somehow weird, but it is a necessary condition. Do you agree with this?
Well, I agree that it's necessary, but it's interesting that we need just third power, not fourth. Not...
Yes. It is proven that in binary case, it is enough to check this. And what is good here? Why this theorem is good? The theorem is good because it shows that the problem in binary case is algorithmically decidable. Why? Because this part is algorithmically decidable. It was mentioned earlier. This thing is just absolutely easily decidable. You just can generate the thing and check. Nothing to. And this thing is also algorithmically decidable. We will see later. In binary case, I mean, it's always algorithmically decidable. It is proven for all alphabets. But for binary case, it's just absolutely simple. So this thing says that it's just the problem is algorithmically decidable. You can just, by looking at the morphism, checking some things for this, for that, tell whether it generates linear word or not. And yeah, in binary case, it is enough here to check just for the third power. We will see that for bigger alphabets it doesn't work like that, and but in binary case it is like this. What is the problem here? Yeah, and the authors of this result did not publish it for a long time. They got it much earlier than in 2024 and 2021. I'm sorry, and they didn't publish it for a long period of time because they thought that they will be easily generalize the result to the bigger alphabets and publish a nice result. But this couldn't be done so easily. So finally they published the result just for 2 letters. Let's see what's the problem with generalizing it. Let's think about alphabets, some bigger than n, bigger than 2. N bigger than 2. Let's have a look at this. What is still necessary for such a word to be Lyndon? Of course, it must be not periodic, because if a word is periodic, purely periodic, here it means purely periodic, not ultimately periodic. Here, if the word is periodic, then the word itself and such, for example, this proper suffix without the first period are the same, are just the same words. So the whole word is not linear word by definition. So this still necessary.
Just a moment. Periodic, you mean it contains, just remind me the definition of periodic.
Definition of periodic here it means purely periodic, that the word the word is periodic if it is an infinite concatenation of the same finite words. Just
okay.
So yeah. It's just the usual definition of purely periodic. You see, because ultimately periodic word can be Lyndon. For example, a word like this. You see.
Well, it reminds me chain fractions. Maybe you may try to use such iterations in order to get chain fractions to approximate something, and maybe it can give rise to some topology on the set of numbers which are obtained as chain fractions.
Yeah, cool. I mean, yeah. you have the topological thinking, yeah, which I lack. Yeah, sure. There might be some, I mean, I don't know the English word. Something to do with other mathematics here, right? Sure. But yeah, let's consider the same problem, but with bigger alphabets once again, and let's try to look at the problem the original authors met while trying to generalize this result. So this condition is still necessary for bigger alphabets. What about this? This condition is still necessary for bigger alphabets. Nothing changes here, because this word is still has this word is its proper prefix. And, so this word must be a prefix of a Lyndon word. This word is so these are still necessary. But the problem here, we meet the problem here, and you commented on this earlier, something, and if I heard it correctly, you did some very, very nice comments, because why does it have to hold? Why does it have to hold? It happens that it have to hold in this case somehow. Yeah, but you will later see that what can be done with this condition. You will later see. But this definitely doesn't have to hold for bigger alphabets, and we can see the example. So the condition of F to preserving the lexicographic order on all finite words is definitely not a necessary condition for F to the power for this morphic word to be infinite Lyndon word in the case of bigger alphabets. And let's see some examples. Easy example, very simple, that authors of the original result got themselves. It was in the paper. So let's look at this word. It starts with A, then we get AB, then we what do we get after AB? It's like ABC. You see, so I mean A, AB, ABC, ABC, B, ABC, BC, and so on. You see, so it will be like A, B, C, B. B, C, like B, C. It's powerful. It is definitely a Lyndon word because we just because there are no more A's in this word. So any suffix starts with something bigger than A. Of course, the order is like this. So this is obviously a Lyndon word, and this morphism obviously doesn't preserve the lexicographic order, because you see here right. So this condition of preserving the lexicographic order of finite words is not necessary, for example, for alphabet of 3 letters, and larger alphabets definitely, because you can create examples like this. Right? The authors themselves in the original paper stated the question like this. I mean, it's a small question. Like we don't know. It's like it's a quote from the original paper. We don't know whether the condition F preserves the lexicographic order on finite words is necessary if F generates a recurrent word. A recurrent word means an infinite word is recurrent. Just some extra things. Yeah, I could have just skipped it, but right. An infinite word is called recurrent if for any its finite substring. I mean, if some finite string occurred in this word for once, it will occur infinitely many times. You see? Such word is called recurrent. For example, this word is not recurrent because once again it's ABC like this. The substring A occurs only once, not infinitely many times. So this is not recurrent. And just the authors of the original result asked, so that they don't know whether this is necessarily if it's recurrent, but it's easy to say, it's easy to show that no, it's not necessary because we can consider this morphism instead. This morphism generates a recurrent word, and it is easy, not as easy as for this, but it's also easy to prove that the word generated by this is Lyndon. It can be done just using the same argument that like an infinite word is Lyndon if and only if it has infinitely many prefixes that are finitely numerals. Here you can just find those prefixes. It is done by hand. It can be done by hand. And also, one may ask, usually asked here in this context questions, what if I want a morphism to be primitive? I mean, once again, some extra thing, it doesn't have to be understood here, but a morphism is called primitive if for each letter there is such k that for each letter ai from the there is such k, let's call it ki, that such word, some power of the morphism on this letter, contains all the letters of the alphabet. Sometimes it's important. Sometimes we only talk about when speaking about morphic words, we only consider primitive morphisms. In some senses, they are better. They're just like a nice morphism.
It looks like irreducibility of presentations.
Yeah, that might be. And you can easily see that this one is not primitive because, for example, for B, it's like if k of B is either B or C. It's B if k is like this, and it's just oops. If k is not like this, so this is not primitive, and sometimes it's just we want to only talk about primitive morphism. We can consider this one. Okay, it can also prove just by hand that this generates the Lyndon word. So it doesn't preserve. It's also easy to see that it doesn't preserve the lexicographic order on finite words because FB once again is strictly bigger than C. So okay, the answer to the question from the original result, from the original presentation is no. But let's see more. Let's see more. Yeah, a proposition from one of the same authors done that was got earlier, much earlier than the result that I'm talking about, is that for binary alphabets, the third condition morphism preserves the lexicographic order on finite words. It's just holds if and only if this holds. So the original theorem looks like this. I mean, just instead of third condition, F preserves lexicographic order on finite words, we just write this. Okay, it was well known before. It was done a long time ago already. So let's have a. I mean, it was needed for me. It's not that important at this point, but okay. The proposition that was made by me is the following. This third condition is redundant in binary case. So you see, the third condition of preserving the lexicographic order on finite word is not necessary in case of larger alphabets, but in case of binary alphabet, it's just redundant. It's obviously necessary, means it's easy to prove that it's necessary, but it just I forgot the English word for that, but I mean, it is true if the first two conditions hold, right? So it is redundant, and you can reformulate the original result just by this. This word is Lyndon. If and only if these two hold. These two hold. We don't need the third condition. Of course, it is necessary, but it's just it just follows from the first two. The proof is not that big. The proof uses this reformulation contains like page and a half. It's not complicated, but the original result now looks much easier. So let me get back to the result, and you just don't need this here. And look, what does it say to us? It says to us the following. We can try to generalize the result in this. I mean, we can try to generalize this result to the bigger alphabets, because the only obstacle, like the only obvious obstacle for the generalization was this, because this is not necessary in bigger alphabets. But we can just get rid of this here and get this result, which can be tried to be generalized for bigger alphabets. Why? Because this is necessary for bigger alphabets. We just don't know whether it is enough. Of course, this constant is different here. We'll see, but let's see what we have. We have a conjecture. Now it is a conjecture that, you know, that might be true. It's not obvious that it's untrue. The conjecture is the following: let F be a morphism over some alphabet of n letters, and such that we can generalize for certain letter A1. We can generate a word starting with letter A1. Here it is A1, of course. It is A1. It is A1. So the conjecture, and then our morphic word generated by the morphism F starting from the letter A1 is a Lyndon word if and only if it's not periodic, and some finite power of morphism F on the letter A1 is a prefix of Lyndon word for some k depending on the length on the amount of letters in the alphabet. It's not 3 because we have some bounds. We can get some simple bounds, and a simple bound is like this. Some simple bounds are like this. K must be at least this, and for smaller k, for this, we have a simple counterexample. You can, I mean, it's easy to prove that is a counterexample. So what means counterexample here? It means that for this k, this this word is a prefix of a Lyndon word, and this is not periodic. The word is not periodic generated by this, and also for this k, this word is a prefix of a Lyndon word, but the whole word generated by morphism F, a whole morphic word, is not Lyndon. So small, so k smaller than this wouldn't fit. And it's proven for all of alphabets right at once by this counterexample. But for this k, now counterexamples were found. I mean, a couple of years ago, when I was trying to do something on this problem, I did a lot of computing with this computer and tried to find counterexamples for this k and found none. So I still low-key believe in this that this conjecture is true, but we couldn't prove it yet, and neither me nor some no authors of the original result or somebody. But it's something to work on. Yeah, I think that's it. I think that's all what I wanted to talk about. Yeah, I also want to give some comments. The original result was proven just so the proof didn't contain any nice ideas. It was just proven, I know how to say it in English, just by some considering different cases and just with no nice trick, nothing like this. Just considering some cases and proving by hand that something holds for these cases, and the proof of the redundancy of the third condition, just the same style. It doesn't have any nice tricks, so maybe for bigger alphabets we need to create something, not just consider cases like we tried before. So then that's it.
Yeah, thank you very much. Are there any questions or comments?
Okay, hello. Hello, everyone.
Yeah, hello.
I have some questions and comments. I have some questions. Did
Right.
you, first of all, this conjecture is mentioned by whom?
This conjecture?
Yeah.
It's mine kind of. It was formulated right after the proof of this proposition. Because you see, the original authors in their paper, they stated this, and they also stated that, and they also noticed that this can be just generalized, can be conjectured, something like this in larger alphabets because of this obstacle. They didn't quite notice that it can be. So they didn't conjecture anything, but right after it was seen that this conjecture can be like it is redundant. The formulation of conjecture was like very straightforward thing to do.
I see. And did you find any connection between that for finding a basing for free algebra? Because if you have one Lyndon word, you can by Lyndon word, you can find a basis for a free algebra. It's a one comment. And second issue, I don't know, you are dealing any times with the two-dimensional words, and not, it somehow is like stop matrix, but not necessary. And recently, not recently, is around of 8-10 years, I will send the chat a paper about two-dimensional Lyndon words. So it would be, it's may interesting if you like, and you can write for me because I'm working this kind of the project in France.
Oh, okay,
So,
okay. Could you please tell me how to write to you? Because yeah, I answer your
and it's
question.
my last question is, may I ask, you are working with whom in Russia? May I ask, you are working with whom in Russia?
I only understand in Russia. I'm sorry.
No, I'm asking who is your supervisor?
Supervisor, Svetlana Kuzmina.
Ah, you are working with Lana. Okay, you are working Lana. Okay, I know.
You know her,
You
right?
are friend.
Oh,
Yeah, you are
yeah.
friend. Okay.
Yeah,
Yeah,
she's
we are
my
friend.
long-term supervisor
Yeah,
already.
I know. We are met each other last year in Marseille. Okay. It's just a second. If you, I will write my email to you.
Yeah, thank you. Because yeah, the answer to your question is no. I didn't try to consider
This is my email.
Yeah.
Because I know it's the Lana, she recently worked about some stuff related to two-dimensional abelian complexity. Is closely related to Nivat conjecture, is a big conjecture in combinatorics on world to finding two-dimensional factor complexity. So I'm sure she's working in two-dimensional worlds. She has got
But
some
she
paper.
never try something like this. But yeah, that would be really.
Yeah. Anyway, you can write to me. It's maybe we can work together.
Okay, I will.
Because I have some things it's more generalized, and that conjecture and that theorem you already mentioned. And sorry, I didn't come in the first after your time because I was in the way. But anyway, it was a night. Thank you. Спасибо большое.
Are there any questions? Yeah, I'm sorry, maybe I missed that. You proved that if F omega is not periodic and F3 is a prefix of a Lyndon word, then it preserves lexicographic order when we have two alphabets.
No,
right?
If this holds, and
if when we have two alphabets, then when it satisfies those two conditions, I mean F omega and F3, then it preserves order, right?
In binary case, only in binary case.
Yeah. Then is it?
Yes, absolutely.
Yeah. for the general case, for more with more alphabets, is it
No,
possible?
Uh-huh.
Is it possible to prove a similar? I mean, if f omega is
No.
not periodic and fk is a
Mhm.
prefix of
No,
a Lyndon
no, no,
words
no.
for
Of course, not just the same example. Look, like this, and wait, like this. You see, and
yeah.
you
I
just
see.
face the same obstacles.
Yeah, I see. Thank you very much. I understand.
Yeah, thank you for
Actually,
question.
the result, it's sorry, I interrupt. The result will not change because it's based on definition of the Lyndon word as a minimum. If you have using cyclic permutation and bit based on the lexicographic order, Lyndon word has a minimum length bit compared to others. So that's why if your size of your alphabet, it would be larger. So it will not change anything.
Okay,
anyway, thank you.
Thank you very much. I think that's all for today. Thank you very much for interesting talk, and let me finish this seminar. Thank you.